Welcome to the Deep Dive. Today we're tackling something really fascinating, DeepConf. It's this groundbreaking method making large language models much smarter, more efficient at complex reasoning.
That's right. If you're working with LLMs, deploying them, researching them, this is definitely something to pay attention to.
Yeah, because the core problem, well, it's always been that LLMs are powerful, sure, but getting them to solve really tough problems like advanced math often means, well, generating tons of different thought paths.
And that gets computationally expensive, fast. We're talking slow, costly processes, millions of extra tokens, huge energy use. It's a real bottleneck.
Exactly, but DeepConf comes in and sort of gives the LLM an internal quality check.
It cleverly uses the model's own confidence signals. Think of it like the model's own intuition about whether it's on the right track. It uses this to filter out the bad reasoning, either as it happens or afterwards.
And the key thing here, which is amazing, is no extra training needed, right?
None at all. No fine-tuning. So it's, relatively easy to integrate. And the results they're reporting are just, well, astounding.
Like what kind of results are we talking?
Okay, get this. Up to 99.9% accuracy on really tough benchmarks like AM 2025. And at the same time, it cuts down the number of generated tokens by up to like 84.7% compared to the standard ways of doing things.
Oh, okay. 99.9% accuracy and massive efficiency gains. That's huge.
It really is a leap forward. Works across different model sizes too, from 8 billion up to 120 billion parameters. Makes this kind of efficient, accurate reasoning much more accessible.
So our mission today is to really unpack how DeepConf pulls this off. How does it get this amazing balance? And what does it actually mean for AI development going forward?
Let's dive in.
Okay, so let's set the stage. Before DeepConf came along, what was the standard way people tried to get LLMs to tackle complex reasoning? And, what were the problems with that?
Right. So the main technique, the one you see a lot, is called self-consistency. It's often paired with majority voting. Some researchers call it parallel thinking.
Parallel thinking.
Yeah, the basic idea is pretty neat. You have the LLM generate multiple different ways of solving the problem, different reasoning paths or traces, they call them.
Okay, so it tries it out, say, 50 different ways.
Exactly. Maybe more, maybe less. Then you look at all the final answers it got from those different paths, and the answer that shows up the most frequently, that's your final answer. Majority rules.
And that works? I mean, does it actually improve things?
Oh yeah, it definitely boosts reasoning accuracy quite significantly. It's been a really important technique for getting better performance out of LLMs on hard tasks.
Okay, so it's effective. But you mentioned earlier it's expensive. What are the hidden costs or limitations that DeepConf is trying to fix?
Well, the big one is just the raw computational overhead. Like you said, generating many paths, that cost adds up linearly. Every extra path means more compute time, more energy. And it can become, frankly, exorbitant. The paper gives this great example. To get accuracy on the AME 2025 math benchmark up from 68% to 82% using a Qwen 3.8b model, they needed 511 extra reasoning traces for each question.
511 extra attempts per question.
Yep. And that chewed through an extra 100 million tokens. Just think about that. The energy cost, the time, the sheer processing power.
Yeah.
It's just not practical for widespread use.
100 million tokens.
Yep.
Wow, that really puts it in perspective. It sounds like you're just throwing compute at the problem, hoping something sticks.
That's a good way to put it. And it's not just the cost. You often hit diminishing returns. Adding more and more traces doesn't always keep improving the score. Sometimes it plateaus or can even slightly hurt performance. But maybe the biggest flaw, and this is where DeepConf really makes its move, is that standard majority voting treats every single reasoning path equally.
Ah, okay. So a really brilliant, elegant solution carries the same weight as one that's completely flawed and nonsensical.
Exactly. A path full of errors can still contribute its wrong answer to the vote, potentially swaying the final result away from the correct one, even if there were some good paths in the mix.
So it sounds like we needed a way to not just generate more thoughts, but better thoughts, or at least figure out which ones are the good ones. How did researchers typically try to, figure out the quality of a reasoning path before DeepConf?
That's the million-dollar question, isn't it?
Yeah.
How do you spot good reasoning? Well, some earlier work did look into this. They tried using statistics from the model's predictions, like entropy or confidence scores for the next token.
Okay, how does that work?
The thinking is, if the model is really sure about the next word or number, it's predicting if its probability distribution is sharply peaked.
Yeah.
That step is probably more reliable. High confidence.
Right. And if it's unsure, spreading the probability out.
Then it might be on shaky ground, lower confidence. These early methods usually calculated some kind of global confidence measure, like an average score across the entire reasoning trace.
So you generate the whole thing, start to finish, and then get one overall score for how confident the model seemed throughout.
Pretty much. It was a starting point, but it had some significant drawbacks.
I can imagine. What were they?
Two main things. First, averaging over the whole trace could obscure confidence fluctuations at local reasoning steps, as the paper puts it. Meaning, like, imagine a long math problem. The model might start off really confident, but then hit a really tricky step halfway through where its confidence tanks. Or maybe it makes a subtle error near the end. A global average might completely hide that crucial dip or mistake.
The average smooths over the critical failure points.
Exactly. And second, maybe more importantly for efficiency, you still had to generate the entire reasoning trace before you could calculate that global score.
Right, so no chance to stop early if it was going off the rails.
Precisely. You burned all that compute, generating potentially garbage paths, only to find out later they weren't good. No way to save resources in real time.
Okay, that makes total sense. You need something more fine-grained, something that works step by step. So DeepConf moves away from that global, after-the-fact analysis.
Yes, that's the breakthrough. It shifts to local, real-time, or at least more localized assessment. It's like checking the quality of each brick being laid, not just looking at the finished wall.
I like that analogy. So how does it measure this local confidence? What are the actual metrics?
Okay, this is where it gets really clever. They start with a basic unit, token confidence, CI. Essentially, how confident is the model about the very next token it's generating at position I?
So looking at the probability distribution for that single next step.
Right. High confidence means a sharp peak, the model is very certain. Low confidence means the probability is spread out. But then they build on this in smart ways.
How so?
They introduce group confidence, CGI. Instead of just one token, this averages the token confidence over a sliding window of previous tokens, say, the last 20, 24, or 20, 48 tokens.
So looking at recent context, not just the immediate next step.
Exactly. It gives a smoother, more robust signal about the confidence in the intermediate reasoning steps. It helps catch those moments, the paper mentions, where you see repeated low confidence markers like, wait, however, think again, signs the reasoning is getting shaky.
Okay, that sounds much more informative than just single token confidence. It's like looking at a whole paragraph's certainty, not just one word's. But what if you specifically want to find the weakest points?
That's where the next metric comes in. Bottom 10% group confidence, C bottom 10T. This is really neat. It calculates the average of only the lowest 10% of all the group confidence scores within a complete trace.
So it actively hunts for the moments of lowest confidence.
Precisely. Instead of letting high confidence parts average out the weak spots, this metric is designed specifically to flag the most problematic segments. They found empirically that looking at the bottom 10% worked really well.
That makes a lot of sense if you're trying to filter out bad reasoning paths. What about for that real-time efficiency we talked about, stopping bad paths early?
For that, they primarily use lowest group confidence, CLEAST. This is simply the confidence score of the single least confident group encountered so far in a trace as it's being generated.
So it's like an early warning signal, if even one segment drops below a certain point.
Exactly. It can trigger an early stop. It's a special case of the bottom 10% idea, but applied dynamically. And one more, tail confidence. This one focuses just on the confidence in the final part of the trace, say the last 20, 48 tokens.
Why just the end?
The rationale is that reasoning quality can often degrade in long chains of thought. And obviously, the final steps are critical for getting the answer right, especially in things like math problems. So checking confidence specifically at the tail end makes sense.
Wow, okay. That's a whole toolkit of confidence measures, much more sophisticated than just a simple average. Looking at the paper's figures, these localized metrics like bottom 10% or tail confidence seem way better at telling good reasoning from bad compared to a global average.
They really are. They provide a much clearer signal to distinguish between correct and incorrect paths.
So the big question then is, how do these smarter confidence signals actually translate into better performance and efficiency? How does DeepConf use them in practice, both for analyzing finished traces and for generating them on the fly?
Right, so DeepConf isn't just one single thing, it's flexible. It works in two main modes. First, there's offline thinking with confidence. This is when you've already generated a bunch of reasoning traces and you want to use confidence to get the best possible answer from that batch.
Okay, so post-processing, how does it improve on just standard majority voting?
Two key ways. First, confidence-weighted majority voting. Instead of each trace getting an equal vote, the vote from each trace is weighted by its confidence score using one of those metrics we just discussed, like a bottom 10% group confidence.
So answers from high-confidence paths count more.
Exactly. It gives more influence to the reasoning the model itself seemed more sure about. But the second mechanism, which often gives a big boost, is confidence filtering. Here, you actually discard some traces before voting. You only keep, say, the top 10% or maybe the top 90% of traces based on their confidence score.
Ah, so you're filtering out the low confidence noise before you even tally the votes.
Precisely. Using the top 10% is aggressive. You're really focusing on only the paths the model was most confident about. This often gives the biggest accuracy jump. For example, with DeepSeek 8B on AME25, using top 10% filtering pushed accuracy from 82.3% up to 87.4%.
That's a solid gain. Any downsides to being that aggressive?
Well, there's a small risk. If the model happens to be very confident but wrong on a particular problem, aggressive filtering might discard the correct answer if it came from a less confident path. So sometimes a less aggressive filter, like keeping the top 90%, which just removes the absolute lowest confidence traces, is a safer bet. It retains more diversity.
Makes sense. And what were the overall results for this offline mode?
Pretty spectacular. Using DeepConf with 512 traces, GPT OSS 120B hit that 99.9% accuracy on AME 2025. Standard majority voting got 97.0%, and just a single trace got 91.8%. So DeepConf basically maxed out the benchmark. Even using lowest group confidence for filtering still gave gains of up to 9 percentage points over majority voting.
Incredible offline performance. But the real efficiency magic seems like it would happen in the online setting, right? Stopping bad paths early.
Absolutely. That's online thinking with confidence. The goal here is pure efficiency. Estimate the quality of a trace as it's being generated, and kill off the unpromising ones early to save compute.
And lowest group confidence is key here.
Yes. Cleese test is crucial because it can flag a problem very early on. The process usually starts with a quick offline warm-up. You generate a small number of traces first, maybe just 16, Nitmayat 16 in the paper.
Why the warm-up?
Get a baseline. You calculate the confidence scores for those initial traces and use them to set a dynamic stopping threshold. Let's call it IS. This threshold might be based on, say, the confidence level of the top 10% or top 90% of those warm-up traces.
Okay, so you calibrate based on the model's typical confidence on this type of problem. Then what?
Then you start generating new traces, token by token. As each trace grows, you continuously calculate its group confidence. If at any point the group confidence drops below that threshold you set during warm-up,
You just stop generating that trace.
exactly, terminate it early, you save all the tokens you would have generated for the rest of that path. You keep generating new paths, and potentially stopping them early, until you reach a strong consensus among the paths that did complete, or until you hit some maximum budget.
That sounds incredibly efficient. What kind of savings did they see?
Huge savings. The more aggressive version, DeepConf Low, cut token generation by 43% to 79% across different tests. On that big AME 2025 test with GPT OSS 120B, it reduced tokens by that staggering 84.7%.
84.7% fewer tokens. That's massive.
It is. Went from over 300 million tokens down to under 50 million. And here's the kicker. Accuracy actually improved slightly, from 97.1% to 97.9%.
Wait, it used vastly fewer resources. A&D got a better score.
The more conservative version, DeepConf High, still saved a very respectable 18% to 59% of tokens, while keeping accuracy almost identical to the baseline. The takeaway is that DeepConf consistently gets you more accuracy bang for your computational buck. It dominates what they call the token accuracy Pareto frontier.
Okay, that's seriously impressive. Getting better results with drastically less compute is, well, the holy grail in many ways.
It really is. It shows how effectively you can leverage an internal signal, the model's own confidence, to achieve tangible, real-world savings in cost and time without sacrificing quality, sometimes even improving it.
So for our listeners, the people actually building things with LLMs or doing the research, what does this mean practically? How robust is this DeepConf approach?
Well, its robustness seems pretty solid. They tested it across a really wide range of models, like we mentioned, DeepSeek, Qwen, GPT OSS, from 8 billion all the way to 120 billion parameters.
And different types of problems.
Yeah, really tough ones. Competitive math like AME and HMMT, graduate level science questions from GPQA Diamond. Across the board, they saw these consistent benefits. Accuracy going up, tokens going way down.
So it's not just a fluke on one specific model or data set.
Doesn't seem like it. It suggests DeepConf is a genuinely practical, scalable solution for making LLM reasoning more efficient, especially when you're dealing with really hard problems that normally require a lot of computational brute force.
Did the ablation studies, where they test different parts of the system, reveal anything particularly interesting about why it's so robust?
Yeah, they confirmed a few things. That warm-up size of 16 traces seems like a good sweet spot for the online mode, enough to get a good threshold without too much upfront cost. They also saw that while the best filtering percentage might vary a bit, that aggressive top 10% filter often did give the biggest accuracy boost, even if slightly riskier.
And what about the local versus global confidence thing?
Crucially, they confirmed that these more complex localized confidence signals aren't worse than just using a simple global average. In fact, they often perform as well or better on accuracy, while enabling those huge efficiency gains, especially in the online setting. It really validates the whole approach of looking deeper than just the surface-level average.
This has been incredibly insightful. DeepConf feels like one of those elegantly simple ideas that has profound consequences, leveraging the model's own internal state without needing extra training. That's powerful.
It really is. And the researchers themselves point towards some exciting next steps.
Oh, like what?
Well, one idea is applying DeepConf in reinforcement learning. Imagine using confidence scores to decide which actions or exploration paths are worth pursuing during training. It could make RL much more sample efficient.
Interesting. Using confidence to guide the learning process itself.
Exactly. Another big area, which we touched on, is tackling that confidently wrong problem. Sometimes models are very sure of themselves even when they're making a mistake. So future work could look into better ways to calibrate confidence scores or combine them with other uncertainty measures to better catch those situations.
Making the confidence signal itself more reliable.
Precisely.
So wrapping this up, what's the big picture takeaway for everyone listening? It feels like DeepConf isn't just an incremental improvement.
I'd agree. It points towards a future where LLMs aren't just powerful reasoners, but they have a degree of self-awareness about their own reasoning quality. They can dynamically adjust their effort, stop themselves from going down dead ends, and conserve resources.
It's like the model becomes its own efficiency expert.
In a way, yes. It's a significant step towards AI that's not just smarter, but also more sustainable and practical to deploy. DeepConf shows us a path where the model itself helps manage its own thought process, making powerful AI much more efficient and ultimately more intelligent.